This week, the plan is to finish with the multipole expansion of the potential and then the problems that we have to do, which is going to be the homework, and then basically problem number 8 and number 9, which are about the multipole expansion. All right, so then this said, what are we going to do today? Today we're going to work on the theory of the multipole expansion of the potential. And why do we have to work on this expansion? Well, so far, what we have done in most of section 2 is basically, well, first of all, defining or finding a way to calculate electrostatic fields when we have finite static charge distributions, and maybe using the superposition principle, we can try calculate the electrostatic field that these distributions of charge generate somewhere nearby. Thank you. Anyway, so all about this section has been basically to go over methods to calculate electrostatic fields. Once we know the charge distributions, be them point charges or one-dimensional, two-dimensional, three-dimensional, we just wrote an expression, an integral, let's say, for the electrostatic field that in principle contains all of the information that we need in order to know the fields once we know the distribution of sources. But then, of course, as we have already seen, these integrals are not always easy to solve. So we have come up with a couple of other methods to calculate electric fields. One of them was in problems of high symmetry to use the Gauss law. And just by identifying or being able to basically calculate the flux of the field over a surface of high symmetry, then related to the charge inside the surface, and just calculate the field, if that was possible. Another option that we have explored is basically calculating electrostatic potentials. You know, the electrostatic potential is a scalar that is basically related to the potential energy associated with the electrostatic field. And then if we can calculate the potential, then all we need to do is basically do the derivative of the potential minus the gradient of it, and that will give me the field. So that is another trick. What we are going to do next, and for this, let me basically share the presentation. The last trick that we are going to play is try to come up with a method to calculate potentials, okay, in the particular case when we are calculating fields very far away from the distributions of charge that are generating the fields. It's only valid again when we are far away. And we will see in a moment why we do this. But more or less, I mean, I would say better how we do this. Why we do this? Because most often than not in real life, we are dealing with problems in physics, and in particular in electrostatics, where we are actually really very far away from the sources. What does very far away mean? Imagine that we actually have a charged body, a body made of atoms. The size, the characteristical radius or length of an atom is of the order of 10 to the minus 10 meters. But we, humans, our characteristic length is more of the size of a meter or a couple of meters. But basically 10 orders of magnitude larger than the size of an atom where electrons or protons are. So this is just an idea for you to realize that very often we will actually be interested in calculating contributions to the electrostatic fields of distributions of charge that are really very, very tiny, which is equivalent to being very far away, when in the perception of the observer, which is typically me in my laboratory. So this particular class of problems actually allows approximating the potential by a series which is related to a Taylor series, and actually mathematically we'll see that what we'll do is doing an expansion, a Taylor series of the 1 over the distance term which appears in the potential, right? And actually trying to capture the physics of my distribution of charge, its symmetry, its shape, right? But from a very, very long distance, okay? And this is what we will call the multipole expansion of the potential, right? And then if we can actually calculate the electrostatic potential associated with my charge distribution seen from very, very far away, then I can calculate the electrostatic field by just doing the derivative of the potential, I mean the gradient, just as usual, okay? So it's a trick to calculate potentials. Basically, what we will do is approximate the potential, and this I'm going to anticipate, of some distribution of charge that has a shape, in other words, has a finite volume, it's not punctual, just as a series which is made of a number of terms. Each one of them tries to capture something about the physics or the shape of the distribution of charge. And what we will find is that my series will have a term of order 0 that we will call the monopolar term, which will be just like having a point charge in the origin with a net amount of charge equal to the total charge of the body, but it being a point charge, you put it there at the middle and the center of mass of my body. And then trying to capture the symmetry of order 2, for example, if there is a separation of the centers of gravity of positive and negative charge because it has some funny shape, like long shape or something, with a dipolar contribution, then trying to have another term capturing any symmetry of order 4, just like if it did look like a square or something, and that would be my quadrupolar term. And each one of those terms is going to be smaller than the previous one. So at some point, I can just truncate my series and forget about it. This multipole expansion, last thing I want to say before talking about it, you can also find it in any problem in physics where you have any sort of interaction that goes like 1 over the square of the distance, like the electrostatic field, for example, in gravity. And those of you who end up studying things like astrophysics and such, sometimes will come up with the quadrupole moments of systems of interest in astronomy. Okay, it's also important, it will also be important in nuclear physics, sometimes for the calculating the magnetic moments of the nuclei. So it actually appears in any place where you have any sort of interaction that has a potential like the electrostatic one. Okay, so it's not just a feature, or it's not a series that is characteristic of only electrostatics. So it's important in this respect. So let's go and talk about it for a bit. What is the multipole expansion of the potential, the electrostatic potential again, outside a charge distribution? Remember, so far, the idea is that we are looking for alternative methods to calculate fields, electric fields, once we know the distribution of sources, for example, a charge density rho. Okay? The fields, let me go back for a moment, actually, themselves, we calculate them using a formula like this. Just it's an integral of something that goes like 1 over the distance, and it might be an easy integral or not. Like I said, a trick that we often play is just calculate the potential that goes like 1 over the distance without a square in it, and also it's a scalar integral, it's not a vector integral like the electrostatic field. And so it might be an easier approach to my problem. And if I can get the potential, then just do the gradient, okay? Sometimes we can do this, sometimes we cannot, and this is why we're actually looking for alternate methods. So for the potential, electrostatic potential itself, remember the electrostatic potential energy per unit charge, right? Even if the integral that we typically have to solve for any charge density, I'm going to do everything in 3 dimensions, but if it was in 1 or 2 or whatever, you know that all you have to do is just change the dimensionality of this integral. So no big deal. What basically happens is that it's not always possible even to do this integral, even if it only goes like 1 over the distance and is a scalar. So like I was saying, and I will insist, we are going to talk about the method that is valid when we are far away from the sources at large distances. By large distances means that the distance where I am calculating the field, this is my vector r, the position over here in this integral, is a lot larger in modulus than any value of R prime within my volume V prime where my sources are. We'll see about this in a moment. And the multipole expansion, I will insist because this is something new for you, is basically, in principle, a mathematical method, but it tries to capture the angular shape or the angular contributions, the asymmetry, if you want to, of my problem, and just express it in a number of terms, okay? So, in principle, the multipole expansion is only a mathematical series. In other words, it's a tool, okay, that tries to approach the actual value of the potential itself. And it's going to depend on the angles, the angular symmetry, the angular distribution of charge within my sources, because like I said, every term of my series is going to try to capture part of the symmetry, okay, of the shape, the morphology, if you want to call it like that, of my distribution of sources. In principle, most times we will work in spherical coordinates, so definitely those shapes will be basically given by the polar or the azimuth angles, right? But we could also work in cylindrical sometimes, but in principle spherical, since we are very, very far away and we see a finite source which is kind of sitting at a large distance, the spherical coordinates work fine. So, like I said, every term of my series that we're going to write down right now will be smaller than the previous one. And at some point, we'll just cut the series short and we'll do an approximation to my potential, okay? So, why do we want to do this? Again, because we are trying to calculate the fields associated with distributions of charge that are not punctual. They are not just a point charge, but they have a shape. However, I am far, far away, okay? So I'm just looking at things that happen in a galaxy far, far, far away. You want to look at it like that. And in principle, imagine that we have some distribution of charge, for example, here on a robot, my R2-D2 right there, and imagine it's actually charged. Typically in the movies, it actually always was just kind of upset about something. But anyway, imagine that this is my source, my rho, my charge density, my V prime is my robot, right here, and it's full of charge. It can be positive at places, it can be negative at other places, it can be neutral in other places. Anyhow, the only thing I will assume is that my distribution of charge is static and it doesn't depend on time. So, like I was saying, the trick here is basically try to calculate the electrostatic field caused by this charged robot, right, in a place R, in a position which is very far from the robot. And again, by very far means that the modulus of the distance is a lot larger than any part of my robot. The arms, the legs, the head, those parts of the robot would be characterized or represented by different values of my vector R prime. Remember, primes are the coordinates of within the sources, okay? So in this particular case, what basically happens is that if I want to calculate the contribution of a little bit of my robot, for example, here, the shoulder, right? Here at R, at my position far away, what I want to consider is this distance between my differential robot, my differential volume, the shoulder of my robot, right there. That would be the distance to the point of interest represented by this blue vector, which would be my R minus R prime. And the funny thing is that since the modulus of R is really, really large when compared to any modulus of any possible value of R prime within my source, that is not, again, a point source anymore, but it's a long source in this case, then R minus R prime will have a modulus that is not quite the very same modulus than R, but it's a lot larger than R prime as well, because it's R minus R prime is the subtraction of R minus R prime, obviously, right? So in our galaxy far, far, far away, at some point, these multiple moments were defined in order to be able to approximate, okay, the potential cost at that very, very, very point. And I just said a word that it's going to be very important here. And I'm talking about moments, multiple moments. Okay, for any charge distribution, we will talk about the multiple moments as those physical quantities that we will define in a moment, okay, that are going to account for the angular distribution of, let's say, the symmetry, the shape of my charge distribution, my source, my charge density. And obviously, the shape of my charge density is going to affect the angular distribution and the symmetry of the electrostatic field nearby or far away, of course. But we just are going to care about far away for the time being. And we will define what we will call the 2 to the nth exponent polar moment as the n+1 term of the multipole expansion for a moment. So we will talk about the monopolar term for the term of order 0. 0 will be the dimensionality. In other words, things like point charges will be treated, or we will talk about them as monopole moments. And then we'll start talking about monopoles are actually single point charges here. Now, as for the second term of my series, if the first one is the order 0, the next one would be order 1, n+1 equals 2. That would be my dipolar moment. The dipolar term is going to be the second term of my expansion, right? And I can anticipate that it's going to describe something like a measure of the, let's say, twofold symmetry of my distribution. In other words, something like a measure of the dipolar moment, if there is any, in my distribution. For example, if there is a separation of the centers of gravity of positive and negative charge, they are not in the same place of my robot in this case, there will be a net dipolar moment. And this second term of the multipole expansion will actually include the physics associated with this twofold symmetry around the dipole, right? And then the next term in my series, the third term, which would actually be term of the second order, because the first one was number 0, second one was number 1, third one is number 2, that would be 2 to the 2, that would be the 4. That's what I would call the quadrupolar term. That will again account for the fourfold symmetry of the distribution, if there is any. And this term is already going to be very, very, very tiny. You can already, if you remember, right, the monopolar term, let's say, well, of course you remember this. The potential of a point charge goes like 1 over the distance, but then the dipolar term that maybe you studied last year, we will see that goes like 1 over the distance squared. So it's already smaller than the first one when r goes to infinity. The quadrupolar term is going to, I mean, what we are going to see in this series, in this expansion, is that every term is going to have an r down there at the denominator, elevated to some exponent, which is going to be first number 1, then number 2, then number 3. So these terms are going to be tinier and tinier and tinier as r tends to infinity. This is why we can truncate at some point, and we'll see how to do this, okay? But this is the number of the names of the terms. Monopolar, dipolar, quadrupolar. The next would be octupolar, because it would be 2 to the third exponent, right? And so on. But actually for electrostatics, the octupolar terms are already quite tiny, so we're not even going to work on them. But we'll go all the way up to quadrupolar. So the question, again, don't forget about it, is how do we calculate the electrostatic field generated by a random charge density in a volume that has a non-even shape, just some funny shape, I don't care. If it's a potato, if it's a robot, if it's a heart, anything. It can have positive charges in some parts of it. It can be negatively charged in some other ends of it. I don't care, one or the other. But we know the charge density distribution, the rho, okay? And we want to calculate the field in a far place. So we need to do some math in order to get there. And don't allow yourselves to be fooled by the math, okay? It's just basically going to be easy. Since in my electrostatic potential, there is a term inside that goes like 1 over the distance, in other words, 1 over the modulus of r minus r prime, can we actually do an expansion of this term when the modulus of r, in other words, this long vector here, is much larger than any possible modulus of r prime, in other words, the maximum of r prime within my sources, for all r primes inside my v prime, in other words, when we are very far away, okay? Can I do an expansion of this thing when R is much larger than R prime for all values of R prime? Well, yes, of course I can. As a matter of fact, we can rewrite the modulus of this vector, R minus R prime, as the square root of the dot product of R minus R prime vector times R minus R prime vector, right? And if I just operate this product, there will be, what I can get easily is the modulus of R to the square, modulus of R prime squared, minus twice R dot R prime, just by operating term by term this product. And then what I can do is just take a factor equal to 1 over R modulus out of the square root by basically rewriting the square root like this. No big deal. So far, I have not done any approximation, only just a little bit of math that should be very, very easy for you all. All right. So then what do I have in here now in my root? I have something that looks a lot like 1 plus a tiny thing. Why am I saying this is tiny? Because remember my assumption, R, the modulus of R, is much larger, but a lot larger, really, than any possible value of R prime. And since R is the denominator in both these products, both of these terms in this square root are going to be smaller than 1, actually much smaller than 1, a lot smaller than 1, as long as this condition here holds. All right? So what I'm doing here now is trying to approximate this term 1 over the square root of 1 plus x, where x is all of this thing, when x is much smaller than 1. And remember the Taylor expansions, you can actually approximate in the vicinity of any point equal where x, my one-dimensional variable, equals a. I can actually approximate my function, any function f, as long as it's a smooth function and it's defined and all of that, as this sum. Okay, a sum for all the way up to, in an integer term n of the nth derivative of f at a, evaluated at a, over a factorial of n times x minus a to the nth power. So in particular, if my function of interest f happens to be 1 minus x to, there should be a minus in here. 1 plus x to the minus 1/2. Yes, sorry. There is a minus there, and I will fix that. The Taylor expansion of 1 over the square root of 1 plus x when x is very, very tiny when compared to 1 can be rewritten, and you can just do the exercise if you want to, as 1 minus x halves plus 3/8 of x squared minus 5/16 of x to the cube plus a number of things. Okay, so now I'm going to use this result, but now my x, this tiny thing like that is here inside my square root in the denominator, is going to be all of this thing, which looks quite funny, but it's tiny, so I could do it. Then what do I get? Atención, sorry. What do I get now? Here comes the math. Okay, the modulus of 1 over the modulus of r minus r prime, which is identically equal to 1 over the modulus of r times 1 over the square root of all of these things. This is what I had in the previous page. In other words, 1 plus all of this bracket minus 2 times r dot r prime over the modulus of r to the square plus r prime over r modulus to the square, all of this to the minus 1/2. And again, so this is going to be my x right here, can be rewritten according approximately, just using the series expansion that I just wrote in the previous slide, as 1 over r, this is the factor in front of it, so that I'm not approximated, but then I have this whole bracket in here, 1 minus 1/2 of all of x right here, plus 3/8 of x squared, plus other terms, okay, of higher order. And then if I actually operate and group these terms that I have here, you can try to do it at home if you want to, and then I will I will put in the virtual campus for you some notes on the multiple expansion by a couple of professors in the University of Sevilla with their permission, of course. These notes are in Spanish, but they can be helpful, particularly if you have any doubts with the math here. But again, just as complementary materials, so you don't even need to look at it if you don't want to, but it could help. But anyway, if I actually operate these things and I regroup terms, what am I going to get? First of all, I have a 1/2 of all of this. This 2 goes away with that one. Then I get a positive term on r dot r prime over r square modulus. This is what I have here. And then I'm going to have a minus 1/2 term r prime over r square. And then I'm going to have to operate this bracket here, which is going to be obviously the square of the first term plus the square of the second term minus twice first term, second term. And so what I'm going to get here is basically terms that go like 1 over r. The 1 over r is here hidden because they have an r here and an r square right there. Plus r prime over r square. And the r prime here is squared. Here I have my r prime over r as well. So this term is already tiny because r prime is much smaller than r. But this term is a lot tinier because r prime is squared and so is r. Okay? And then over here, I'm again going to have a term where I have r prime over r to the 4th. However, I have an r square here. So this term really, when I actually operate this square, is going to go like this one, like r prime over r squared. It's okay. It's tinier than the first one. I will add it up to this one. And then I also have a term here, which is going to be r prime squared over r squared squared. So that's going to go like r prime to the 4th, r prime, over r to the 4th. And then I have twice the first term and the second term, which is going to end up going like 1 over r to the 4th. And here I have an r as well in the top. So in the numerator, so that's going to go really like 1 over r to the cube. And then I have an r prime and an r prime squared. So this is going to go like r prime cube over r cube. And the only reason why I'm saying this is for you to see that you can actually do this if you want in a piece of paper at home slowly, and it's not very difficult. What you will see is we're going to get a number of terms where I have, other than this one in front of it, terms that go like r prime over r. The next one is going to go like r prime squared over r squared, and then r prime to the cube over r cube, and then things like go like r prime to the 4th power over r 4th. And since r prime is always much smaller than r, those terms are going to be tinier, 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 and tinier. So I'm actually going to cut my series short in the term where I have r prime squared over r squared. And you would say, wait a minute, this is r prime squared over r to the 4th. No, there is an r squared here. So in reality, this second part of this goes like r prime over r, all of it to the second, to the square. And then here I also have an r term to the square. So in reality, this term goes like r prime over r squared. No 4th or 3rd or cube, no. Okay, so I'm basically truncating there. And then I'll have things of the order of r prime to the cube over r cube. But again, this is already going to be much tinier than this one. I'm going to cut there. So I have here a term that goes like r prime over r to the 0 exponent, so it's 0 power, that's a 1, r prime over r prime square over r square. Okay, so this is a little bit of the terms that I'm getting with my expansion. Interestingly for you, I was saying that somehow the terms in my expansion are going to try to capture the shape, or let's say the angular distribution within my density of charge, my sources, in my V prime. Do I have an angle in here? Well, of course I do. It's hidden, but it's there. If I actually have a dot product here of r, remember the vector of this point far, far away where I am calculating, dot r prime, the vector of any possible piece of charge distribution of sources, here, if I'm calculating the dot product of these two, I have a cosine of alpha. Who is alpha? The relative angle between those two. So yes, there is an angle hidden in here. And as a matter of fact, if you try to look in the book of Griffiths, there is in chapter, I think number 3, which is the one about electrostatic potentials, that I told you we are not going to see, at least not all of it. Okay, but there is a section of it on the multiple expansion of the potential that you can read. It's going to tell you about directly the terms of the multiple expansion of the potential in a different form. They will not write things, Griffiths doesn't write things like I am here with dot products and such, but he already goes into writing the different powers as powers of the cosine of the relative angle within the charge distribution. So it's a little bit different to what we are seeing at the very end. The physics of each term is going to be the same, but the way it's written mathematically, it's different. Now, these notes that I was telling you from the University of Seville, they actually write things this way. This is what I want to have them in the virtual campus in case the Griffiths book doesn't ring any bells to you, because the notation is different. Okay, so you can still look at the math in some piece of some chapter written carefully by someone with actual letters and sentences, not like my slides. But anyway, I like things written this way because mathematically, at least for you, is not so difficult to get from here all the way out to this expression, which is not very user-friendly in principle, but mathematically is quite straightforward. And like I said, here is the angle, here is the cosine of the angle squared. Okay, so we have all these terms that we are going to put now into my expression of the potential, right? So let's do it. If my potential, in principle, was looking like, let me go back, sorry, for a moment. I hate when people do this. Okay, but here it is. This was my integral of the potential in principle. When I substitute my 1 over r minus r prime, the distance, by all of this expression that I just got, what I'm going to get is a sum of terms. Each one of them is going to correspond, let's go again forward, to this one, 1 over r times 1, so that's 1 over r. The second one is going to be r times, well, r dot r prime over the modulus of r squared. But remember, I have this factor in front of it, 1 over r, so this is going to go in. And then I'm going to have a third term that is going to be all of these products and here over 2 times r to the 5th exponent, to the 5th power, sorry, because I have a 1 over r in front of it, don't forget about it. And then I will rewrite my potential as a sum of terms that look like this. And what do I have in here? First, of course, first term, second term, third term. 1 over 4 pi epsilon naught, that's the one, the constant that I had there in principle in the beginning. And then 1 over r, and of course I have the charge density and the differential volume in the integral. Okay, that was my first term, 1 over r. Remember, this one here, over r. Second term would be 1 over r to the cube, and then on top, on the very, very top, I would get r dot r prime. Do I have this? Yes, here is my r dot r prime. Now, I took the r out of the integral because the integral is in prime coordinate. Remember, here is my dv prime. So I am integrating, I am doing this calculation for every little differential volume in every possible r prime position within my sources. In other words, r prime moves all the way to sweep, to probe every possible point within my sources, but r stays constant in this process. So I am not integrating over r, I'm integrating over r prime. In other words, r can go out of the integral. And I'm actually doing it. So I have here my r over the modulus of r to the cube, and then whatever stays in the integral is the rho, the charge density, which is a function of r prime, and of course times r prime, differential volume. Next term, if I go back for a moment, what did I have? In my expansion, this term here. D would be a total, if remember I have this r in front of it, so it would be 1 over twice r to the 5th power, and then at the very top of the expression I will have all of this expression here, 3 times r dot r prime squared minus the modulus of r prime squared times the modulus of r squared. This is what I have here. Same idea. I'm going to take the constant 1 over modulus of r out of the integral, obviously to the 5th power, because I'm integrating in prime coordinates, and I'm going to leave everything that depends on r prime inside the integral because I'm integrating in prime coordinates. So I have the rho, the charge density, and then everything else stays inside because I have r's. Yes, I do, but they are actually multiplying r primes. So this term, I'm going to leave the whole thing inside. This thing in here is what I'm going to call my multipole expansion of the potential. The first term, I'm going to call it V1. That is the monopolar term. Second term, I'm going to call it V2, dipolar term. Third term is going to be V3, quadrupolar term. And we're going to talk about each one of those in a moment. But it's very important for you already to notice these integrals look kind of not very user-friendly, really, but they actually, these terms, they are, each one of them is a lot smaller than the previous one, because the first one, V1, goes like 1 over the distance. The second one goes like 1 over the distance squared. The third one goes like 1 over the distance to the 3rd power. And remember, we have an r square and r prime. Oh, there is a square missing in here, I think. Let me wait. Yes, there is a square missing in that expression. I'll fix that. Not right now, but I'll do it. Okay. So each one of them, when r is very, very, very large, goes to 0 much faster than the previous one. So therefore, we can do a truncation, and actually maybe we will only consider the first term sometimes, or maybe the first and the second. Not very often we'll go to the third one. But sometimes it will be important, and we'll see examples. Okay? So this is my multiple expansion of the potential. V1 is the first term, V2 will be the second one, V3 will be the third one, and then we'll have octupolar, and we'll have higher order terms, V4, V5 if you want to, but we're not even going to look at them because they don't tend to be very, very important. They are really negligible in most important and relevant cases for us. All right. Carlos says there is a yes, there is a 2 missing in the quadrupolar, and since Carlos is asking, I'm going to fix it. Yes, so like I said, thank you very much, Álvaro. My monopole term, what does this thing look like? It actually must look awfully familiar to you, because what do I have here? 1 over 4 pi epsilon naught r, the modulus of the distance. The distance from where? Hey, from the origin all the way out to the point when I'm calculating. Okay? Times the integral of rho dv over the volume of my sources. But what is this integral? It's just what we typically call net charge, total charge of my distribution, isn't it? The integral of the charge density, right? In other words, this term here is just the total charge, identically equal to the net charge in my distribution. In other words, V1, the monopole term of my multiple expansion, is just the potential, represents just the potential that the point charge, because this is the potential of a point charge, hey, Q over 4 pi epsilon 0 distance is a point charge, placed at the origin, but this charge should have the same net value that the total charge in my charge density, in my 3-dimensional distribution. So the monopole term is basically, it does represent the potential that a point charge placed at the origin would generate around it, as long as the net value of this point charge was the total charge in my distribution. Okay? So this term here, the integral of rho dv, in other words, the total charge, is what we call the monopole moment. hey, it's a point charge. Okay, it's a kind of, we physicists like calling things funny names. So the total charge of my distribution is just a monopole moment. Okay, and it is always going to be the dominant term in my potential, the dominant contribution to the physics, to the electrostatic field nearby my distribution. Okay, it represents the potential of just the total charge placed at a single point, the origin. It's going to be the dominant term because it goes like 1 over the distance. The next term is going to go like 1 over the distance square. Is going to be much smaller. Okay, what are we trying to say here? That if I have a charge distribution with a net value of the charge that is finite, in other words, it's not zero because it doesn't have positive and negative charge, for example, placed at different parts of my charge distribution that cancel each other, or like the charge distributions that we have seen in the problems where we had some negative charge in the origin surrounded by a positive density of charge, or the other way around in our Yukawa potential, right? In those cases, the net charge was zero. But if we have any other situation where the net charge of my body happens to be finite, in other words, not null, then the dominant contribution to the potential and therefore to the electrostatic field, as long as I am looking at things very, very far, far away from a distribution, is going to be just like the potential of a point charge. Of course, a charge of that has a value equal to the net charge of my distribution. And it makes an awful lot of sense because the more far away, the more farther away that I move from my distribution, the tinier and tinier and tinier and tiniest I see it. And to me, it starts looking like a point charge. Place where? At the origin. By the way, I'm actually assuming all the time that I'm putting the origin close enough to the center of gravity or the center of mass of the center of charge, if you want to, of my charge distribution. But if I am very, very, very far away, both those two tend to look the same anyway because they are so close to each other. Because if I see my charge distribution super tiny like this in the distance, okay, then obviously I cannot tell I'm just putting the origin right there at the charge distribution. I cannot tell where the center of mass is within my charge distribution because I don't resolve it anymore. I just see it so tiny. It makes sense that mostly the electrostatic field generated by a charge distribution when I'm very far from it looks like a point charge. Okay? So, to a very rough approximation, which works so much better the farther away that I am from my point, the charge body can be envisaged just like a point charge. In other words, my whole body collapses to a point and all of its charge is located just right there. And that's where I put my origin. So I see the potential and the field of a point charge. In other words, charge distributions, when I am very, very, very far from them, look like point charges. Surprise, surprise. And in principle, if my distribution was actually had a net value of the charge different to zero, that would be all I would need to know. If I'm far away, that's it. That would be like a point charge. And this is why when we actually talk about problems where we have point charges sitting in different places, so far, we have gone all the way to actually writing those point charges as Dirac deltas and everything. So we have a mathematical formalism, right, that sort of reproduces the physics of a point charge. But we don't really care if the charges are actually point-like, zero-dimensional, or they have some super tiny points, but with finite sizes small enough that I actually think they are just zero-dimensional objects. I don't care because the physics is the same. Okay? But then, what happens when I have charge distributions, like our Yukawa potential last week or any other distribution, where the object exhibits some charge density, which is inhomogeneous or whatever, but the net charge of it is zero. Because there is as much positive charge in some places as negative in other places. And the total sum of the charge in my body is zero, but the body is charged. And therefore, it actually generates some field around it, like, for example, a dipole. If I have a positive and a negative charge very close to each other and very, 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 very far away, they sort of cancel each other, but there is a dipolar field around it. In this case, the monopole moment would be 0. And if I think of my multipole expansion, then I will have to go and look at the second term. The first one would cancel out, then I would look at V2. So let's talk about V2 for a moment. V2 is what we call the dipole term. And this thing inside the integral, rho times r prime, integrated over the whole volume of sources, is what we call dipolar moment of my distribution, P. Okay? The dipolar moment P, which for a number of point sources can be calculated as the sum of each Q, Q1, Q2, Q3, whatever, times its position R1, Q1, R1, plus Q2, R2, plus Q3, R3. When I have a finite distribution of charge over a volume, what I do is the infinite sum, which is an integral over the sources of charge times position. But charge dq is here, rho dv, and the position is r prime for every dv. This is my dipole moment, the very same dipole moment that you saw last year, what we call P in physics. So if I define this dipolar moment, P, this way, I can rewrite the dipole term, the second term, V2, as P dot R over 4 pi epsilon naught R to the Q. So again, this term, the dipolar term, is going to be characteristic of the shape of the charge distribution, and it, for example, this term tends to be finite, in other words, non-zero, for example, in situations where the centers of mass of positive and negative charge are separated from each other. And then a dipole moment appears going, remember, from one charge to the other one. This is my P in this case. So an object, for example, imagine we had a cylinder that had more negative charge on top and more positive charge on the bottom, that would have this integral not vanishing, would have a finite dipole moment P. We can talk about dipole moments also for distributions of charge, not just for point charges. So in this case, what does the dipole term represent? Well, it is exactly the potential here that would be generated by a dipole of magnitude quantity equal to P, this P, placed at the origin. If we have a situation where right at the very origin I place a dipole P, this dipole is going to generate a field around it. For point charges, like I said, it's very easy to calculate the dipole moment, right? For finite distributions, it's a little bit more complicated, but see basically the dimensions are the same. Q rho dv times position, sum for my whole body, okay? And I just sort of place this dipole at the origin, and then what sort of potential do I get around it? This P dot R over 4 pi epsilon naught R cube. In principle, this term decays, goes fast to zero, faster than the monopole contribution, because it goes like 1 over R squared, R over R cube here, okay? And in situations where I have charge densities that have a net charge equal to 0, but, for example, they have their centers of gravity of positive and negative mass separated from each other, then at sufficiently large distances, I can approximate the electrostatic potential and also the electric field just like that of a dipole placed at the origin. Okay, and what would be the value of P, the dipole moment? Well, whatever the charge density looks like, just do this integral and calculate, and see that this integral is actually a lot easier than integrals that go like 1 over the distance, because the distance is just multiplying the charge density there. So, okay, yeah, we have an integral, but it's an easier one in principle. Okay, so in charge distributions where I have no net charge, the potential and the electrostatic field around them often can be seen as behaving like a dipole when I am far, far away from it. Just a dipole, a regular one. Positive charge, negative charge, and there is a field around it. Okay? Oh, next term. Imagine I have charge distributions that have a net charge equal to 0, and then they do not have a separation of the centers of gravity of positive and negative charges. For example, imagine we have 4-point charges in a square. Imagine let's have some square, just like problem number 8, actually. Let me go forward for a moment. Oh, yeah, this is horrible, I know. right there, I want to go there. Here, imagine we have 4-point charges, like this one, placed each one of them at the vertex of a square of side, whatever, A or 2A or whatever, and their values are Q and Q over the one diagonal, minus Q and minus Q over the other one. And they say, calculate the electrostatic field that this object generates somewhere far away. This body has no net charge because the net charge is Q plus Q minus Q minus Q, 0. This system has no net dipole moment because the center of gravity of charge, of positive charge, is in the origin, and so is the center of gravity of negative charge at the origin. There will be no net dipole moment here either. But there is an electrostatic field around it, yes, because those charges are not at the origin. They're actually separated from each other, so they're going to have some contribution. They are sort of going to cancel each other at some point. Yes, they will, but it's not like having no charge at all. This is the typical sort of example where you have a quadrupole like electric field. So let's calculate it by looking at the quadrupole term of the expansion of the potential. It's a bit mathematically a bit trickier, but the physics is just that. Let's look for a term that captures the next degree of symmetry. We already had the 0-dimensional symmetry, let's say like a point charge at the origin. Next, we have a twofold symmetry, like whatever captures the twofold, let's say, shape of my charge distribution, if there is any. Imagine there is none, like the example we just discussed. Well, then let's look for some term that captures any fourfold change in the shape of my body. In other words, do things change when I rotate them for like 1/4 of a turn and then another? Yes, the example we just discussed does change when you rotate it 1/4 of a turn. It does not change when I rotate it half of a turn. There is no dipolar term, like I said. So we need to be look just with a larger, let's say, magnifying glass and go to some finer detail. That's the quadruple term. And this quadruple term that we just wrote a moment ago looks like this. And now this integral is not so user-friendly anymore, right? What is this? Well, in order to come up with some expression that we can actually use for calculating, let's do a little bit of math. And again, the details of all of these are in these notes that I will post in the virtual campus for you. Even if they're in Spanish, they will be helpful. Okay, let's just rewrite the coordinates, our Cartesian coordinates for a moment, just for the sake of notation, not as x, y, z, but at x1, x2, x3. Just to get to an expression with a more compact notation, no big deal. x1 will be x, x2 will be y, x3 will be z. And of course, for r prime, x prime, y prime, z prime will be x1 prime, x2 prime, x3 prime. No big deal. In this particular case, I can rewrite what's inside the integral, this 3 times the dot product of r times r prime minus the modulus of r prime square, modulus of r square, as 3 times, what do we have here, the dot product, first component times first component plus second component times second component of the vectors plus third component times third component. This is what I have here. The sum when I goes from 1 to 3 of xi times x prime I. First times first, second times second, third times third. No big deal. And all of this has to be squared, okay? Because there are squares here. And then Oh, there is a square missing here. And there is a square missing here too. Sorry. Just the math for a moment. This is just some mathematical expressions, no major physics into it. But then we have here r prime squared times r squared, the modulus. So we can rewrite this expression as r prime squared, just factor, and here is the modulus of r squared. That would be x1 squared plus x2 squared plus x3 squared, in other words, x squared plus y squared plus z squared. And each one of those is going to be multiplied by this factor. So this is a way of rewriting this thing. And now I can do something which is basically, since this is going to be a square of this sum, if you actually put two subindices there, I and j, each one of them goes from 1 to 3, because each one of those is going to sweep the three coordinates x, y, z. When you actually do this square and you go term by term, multiplying first one, second one, first one, third one, and then second one, first one, second one, blah, 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 then the first term can be rewritten this way. You're going to have a cross product of xy components, xy prime components, xj components, and x prime j components, where I and j go from 1 to 3. So that's the first one. And the second one, I'm going to write it in this form for a moment. I'm not doing anything, but I also want to come up with some double sum over I and j, so I can put everything in the end together in one single double sum. And for this, what I'm going to do is rewrite my xy square, xi, sorry, no, y, no, I square term as xi, xj multiplied by this function. Do you know this function is the delta, the Kronecker delta? The Kronecker delta. Have you seen this one before? No? Yes? Nobody says anything? No, in math. Okay, fine. It's a wonderful function. I love deltas, and in particular Kronecker deltas. It's a function that equals 1 if I equals j, and is 0 if I is not j. Anyway, so then I can do xi square is just like xi, xj delta ij, because this term takes care of making this product go to 0 if I is not equal to j. The only reason why I wanted to rewrite this thing using the Kronecker delta, which is just a mathematical tool, no big deal, is so that then I can put all of those things into the same double sum. And also, since in both terms I have xi first and then x prime xj over here, and here I have xi and xj, I can put the xi and xj like factors, and then put everything else in a big bracket right there. And since these are not vectors or cross products or anything, it doesn't really matter if I have my xj first or second, who cares? I'm just going to make sure here that I'm summing over all possible combinations of subindices, so no big deal. In other words, this whole term in there can be rewritten for my x, y, and z components, where now x is x1, y is x2, z is x3, like this funny term. Why do I want to do that? Because in this case, now I can go into my integral, and the thing that is in there becomes all of this. And I'm going to rewrite my potential in this way. First, my 1 over 8 pi epsilon naught, this 8 is already is correct now. I had forgotten about the 2, but then I put it back at some point. So this is good. 4 pi epsilon naught r to the 5th exponent. This is all of this term here. And then I'm going to rewrite all of this integral as the sum where I goes from 1 to 3, over the sum of j going from 1 to 3 of xi, xj, remember these are just x, y, and z's, times a matrix that I'm going to call qij. A matrix. And what is this matrix element? Qij. Well, because it's a matrix because both I and j go from 1 to 3. simultaneously. Well, the integral of rho, my charge density, times this factor in there that I had come to the realization that I could transform this thing in here as this sum. Since the sum goes over the three spatial coordinates, it can go out of the integral, so it commutes with the integral, no big deal, this is why I take it out, and then everything else stays into the integral. Okay? This Qij that I just wrote is what we are going to call this matrix, because at the end of each one of those is a matrix element. We have the Q11, Q12, Q13, Q21, Q22, Q23, Q31, Q23, Q33, and each one of those is just basically QXX, QXY, QXZ. Those would be Q11, Q12, Q13. Next row, QYX, Q21, QYY, Q22, QYZ, Q23. Third row, QZX, Q31, QZY, Q32, and QZZ, which will be Q33. This is a matrix, and we call this matrix a quadrupole tensor. A tensor is a multidimensional number. You have not seen tensors so far, I think, at least not most of you do. But in 2 dimensions, a two-dimensional tensor is a matrix. A zero-dimensional tensor is a scalar. Okay? So tensor is just a general way of calling mathematical objects that can be multidimensional. If they are zero-dimensional, they are just numbers, digits, right? A 2x2 tensor is a matrix. Can be a 3-dimensional matrix, a 2-dimensional matrix, but it's a matrix. Okay, so we call this quadrupole moment tensor because it's a matrix with 9 elements. It's a 3x3 2-dimensional matrix. And again, the value of each one, the net value of each matrix element is going to depend on the integral of the charge density times a number of spatial variables that basically just depend on the shape of the charge distribution, because x prime here is basically x prime 1 is x prime, x prime 2 is y prime, x prime 3 is z prime. So here what I have is basically products of things that depend on x prime, y prime, and z prime, and here I have the modulus of r prime, which is the square root of x prime square plus y prime square plus z prime square. So these are just quantities that depend on the shape and the geometry itself of the charge distribution. The integrals might be easier or more difficult to do. Yeah, they could. But we are going to see examples. These are basically just integrals of polynomial expressions. And they are really very easy to solve, especially if you have charge densities that are uniform and they go out of the integral. Okay, so each one of those defends the quadrupole moment tensor, and then this expression, this V3, the quadrupole term of the potential, can be rewritten like this, because this sum over y and j, I and j go from 1 to 3, can be rewritten as the product of a vector. And now I am undoing my change of notation from x1, x2, x3 to x, y, z, just for practical purposes, because I think x, y, and z are more visual to you. What do I have? My constant here, and then this is just the product of my vector x, y, z. Oh, this should be a z. So anyway, x, y, z times my quadrupole tensor with its 9 components times x, y, z. In other words, you can write this as the R transpose Q R over 8 pi epsilon naught R to the 5th. Okay? It looks funny, but at the end of the day, this thing over here is a number, it's a scalar. Because when you do this sum, what you get is a sum like this, where you would see this thing times this thing times this thing times this thing, and then that will be a vector that will be horizontal, and then you will sum that vector, multiply by the second thing. That's it, it's a number, it's a scalar. And that is the quadrupole contribution. When you have 3-dimensional charge densities and you undo the xi, xj, when I and j go from 1 to 3, back into xyz coordinates, you can rewrite all of those expressions, qxx, qyy, qzz, qy, all of them, just like this. And see that these are integrals of polynomial expressions. This is not difficult, especially if you have charge densities that might be homogeneous or might not be very difficult. It's not really complicated. It's boring. Yes, it is boring. But it's not complicated. By the way, if we have point charges like in exercise number 8 that we will do tomorrow, then these integrals just become sums, finite, discrete sums. Okay, but they are not integrals anymore, but for the rest, we will be summing over the 3 components of the R prime position of each charge. Okay, so then in this case, things become sums, not integrals anymore, but then again, we have the very same results there. We'll do an example, like I said. Okay, now interesting things about the quadruple tensor is that first, it's a symmetric tensor. And it's not difficult to see that qyx equals to qxy if we go back to the definition of the different component right here, because there is no difference right there if I just invert i's and j's. No, doesn't make a difference. And second, it has 0 trace. If I sum qxx, qyy, and qzz, it doesn't take a lot of work to see that these take care of canceling each other. So in principle, our tensor of 9 components will only have 5 independent components. And in problems of high symmetry, which are the ones that we are going to basically use all the time, if I put my axis of symmetry along the z direction, just for the sake of choosing a direction that everybody are doing it the same way, then all elements can end up being rewritten in terms of the qzz. In other words, the last element of my matrix. And this is why typically when somebody talks about calculate the quadruple moment of a distribution, what they typically mean is that you have to calculate qzz. And then if you know qzz, then you know everybody else too. We'll do an example of this. It will be problem number 9. Those we'll do tomorrow. So why is all of this important? Because in cases where we have charge distributions where the net charge is 0 and the dipole moment is 0, because there is no charge separation, like this number 8 problem that we had next, right here. There is no net charge, there is no net dipole here. Then V3 actually becomes the first component that captures some contribution to the electrostatic field that is not 0. It might go to 0 very fast. Yes, of course it will. Quadrupolar fields go down to 0 very fast. They go like 1 over r squared. Sorry, cube to the third exponent, but they are not 0. So sometimes we really want to calculate those fields. Okay? And it becomes the dominant term at larger distances in this particular case. Just a couple of things before we finish with the theory. First of all, about our moments. The monopole moment, Q, the total charge of my system, is independent of the origin of coordinates. If I want to calculate the net charge of a distribution, I just calculate the net charge and it will be 1 coulomb minus 2.5 minus 1.60 to the minus 19, whatever, regardless of how you calculate the integral, and by how you calculate, I mean where you place the origin of coordinates. Important. Now, the dipolar moment P does depend on the choice of origin. If I calculate dipolar moments with respect to a given origin O, or with respect to a given origin O prime, then those dipolar moments are going to be different. And in particular, the difference will be exactly equal to Q times the segment that goes from O to O prime. So the dipolar contributions depend on the origin, and it typically is very convenient to choose an origin that is exactly the center of gravity of the two let's say positive and negative contributions to the dipole moment. You just put the origin in the middle for practical purposes. At the very end, when you calculate the electrostatic field or the electrostatic potential, the field that you get to is going to be the same. Okay? It has to be the same. So at some point, different dipole moment will find ways of sort of canceling terms. So at the end of the electrostatic field does not depend on the origin, but be careful, the dipole moment does depend on the origin. And the quadrupole moment does not depend on the choice of origin either. Okay, when you do that integral, since it has always full of squares and stuff, then things cancel out. Anyway, that was just a comment. So what we'll do tomorrow is basically exercises number 8 and number 9. And in principle, I want to do them, I'm going to do them here from the office, because we really have to comment a number of things that you have to understand. Okay, and I was not very pleased with the result of last week's class from the Blackboard. They just go too slow, things don't work. We had those were questions both in the ordinary and in the extraordinary exams. So I really want you to understand how you do these things and what do they mean in practical purposes, okay? So we'll work on those tomorrow. And then on Thursday, we'll work on the dipole term in particular, which will be our introduction to section 3. And then we'll also fix the homework, and that we'll do in the classroom, okay? All right, then. That's the end of it. See you tomorrow.